So our next speaker is David Webb. We'll be talking about under what reducibilities are KLR and MLR Medvedev equivalent.
Okay. I want to thank the organizers for having me. I'm very excited to speak to you all today about a recent project of myself and my advisor, Bjorn Hansen, which sprang from a partial result that we obtained last summer. So to start, the sort of setting for this talk is a big open question in algorithmic randomness, which is, are KLR and MLR really the same notion of randomness? For the purpose of this talk, I'll mainly define MLR on the next slide. What we really need to know is that these are not presently known to be equal, and that, but we have some partially known results. We know, for instance, that Martin-Low randoms are Kolmogorov-Loveland random, and so we have a strong reduction in the sense that, well, identity is a reduction in one direction. So that's certainly a helpful result. In the other direction, we only have, or at least recently only had a weak reducibility, in that if you hand me a Kolmogorov-Loveland random, I don't know which, but one half of it is going to be Martin-Low random. So there are two possible reductions, either take the even bits or take the odd bits. But since I don't know in advance which to use, I only have this weak reducibility. And so Miyabi asked, is there actually a uniform reduction from KLR to MLR? And Bjorn was able to say yes. In fact, in his review of Miyabi's paper, that there is in fact a strong reduction. And so I want to go through that proof for a moment and talk about this proof technique and whether we can get anything else out of it. That's sort of the thrust of the talk. So the technique starts with just a guess. So, all right, I think A0 is my random section. And what does that mean? Well, a Martin-Low random is incompressible in a sense. It should have very complicated prefixes. No matter, there's some constant C, so that no matter what prefix I'm looking at, the smallest program that outputs that prefix is always of at least length n minus C. So helpfully, because I'm searching for programs to halt, I have an approximation of Kolmogorov complexity. I can just start seeing which programs have halted by stage S. So really, this statement here could have a little extra quantifier in it, which is very, very helpful, because I can test all these things at finite stages. And if there's a failure, flipping around my quantifiers, it would be witnessed at a finite stage. So I'll take a guess for my constant C. I'll start at 0. And then I'll just kind of start looking. I'll start asking about prefixes and seeing if I ever witness a failure. At every stage, I'm assuming maybe A sub I is my random. And so I'm trying to spit out bits of A sub I. For instance, I'll start at A sub 0. But eventually, if there's a failure, I'll witness it in finite time. I will see a prefix that is too compressible for this constant. At that point, I need to, well, increase my constant for one thing. It's possible that I do have the right half, but that I just have the wrong constant. But it's possible I have the wrong half. So I should also switch and start outputting bits from the other half. And I'll go back and forth like this. And eventually, I will find a constant that works, because I'm guaranteed such. I'm told that it exists. And once I do, there will be no more prefixes. There will be no more stages where a failure ever happens. And so for the rest of the algorithm, I will only be spitting out bits from that one half of my oracle. So that's the proof that we get a strong reduction. And I wanted to look at it for just a second, in that it's a Turing reduction is what we wanted. But in fact, it's a little stronger than that, because I don't ever make use of an unbounded amount of the oracle. In order to output the nth bit, I'm trying to output the nth bit of one of the halves. So I really just need 2n bits from the overall oracle. So this is not just a Turing reduction. This is a truth table reduction. This has bounded use. So we got a little bit extra for free, which is very nice. So the question might be, can we improve this at all? There are a number of reductions that are stronger than truth table. Maybe the most famous, maybe 1 reductions or many 1 reductions. But there are a handful of reducibilities in between. And I'd like to know whether or not I can discount them, whether or not this proof technique can be used further, or if I need a new one. So toward that end, I'd like to rephrase truth table reducibility, not talk about bounded use, but actually talk about truth tables. That I'm essentially pre-registering all of my questions. All the questions I'm going to ask the oracle come preloaded in a computable way. So I'm going to list all my truth tables in some uniformly computable list. And they have certain variables that I'm indexing by. And I'm interested in saying that my real satisfies a table if when I replace all of its variables with bits that I lift from X, and then I see whether that is actually true or not. All right, so this is what a truth table reduction really is. And viewed this way, maybe it's a little more obvious what kind of changes I could make. Right? It becomes clearer what the other reducibilities might be. I can, I can ask only certain types of questions. I can restrict the types of truth tables I have access to, or I might even bound the number of queries I'm allowed to make. But the proof that we did on the previous slide didn't really use KLR. Right? It did in a sense, but the property it was really making use of was this half randomness. So I'm introducing this new mass problem of either of some existing mass problem where one half of the real belongs to C, but we don't know which. And so we are trying to uniformly output bits in a certain mass problem, given that I definitely have some of them, but I don't know where they are. I don't know whether it's on the even half or the odd half. And so if I can find additional reducibilities where this works, that would strengthen the result that I have about KLR and MLR. Because obviously it's possible that, in fact, those are equal and that all of this work is redundant, which would be great, but we don't know that yet. But it's also possible, and in fact, I'm going to show that this particular technique of using either MLR, it got us truth table reductions, but it can go no further. So none of these, apologize, my dogs seem to know when I'm giving a talk and decide that's when they want to be active. So, excuse me. Anyway, these are some various reducibilities that are related to truth table reductions. And some of them, as I mentioned, are very common. We see one reductions and many one reductions in a number of settings. But these D, C, and P, for instance, I was unfamiliar with until recently. Those are disjunctive, conjunctive, and positive reducibilities, where I only allow, for instance, or statements in my tables, not even any knots. Down at the bottom, BTT1 is just like a many one reduction, but I'm allowed to flip bits. So I'm allowed to use knots. And many of these come from post lattice, certain incomplete collections of connectives, whereas truth table is I'm allowed any connectives I want. So I'm going to show, in order to knock out the whole table, that sort of column third from the right, all of those fail. Positive reducibility won't work. Linear reducibility won't work, and bounded truth table reducibility won't work. And so maybe other techniques will for KLR, MLR, but this either notion is, while interesting in its own right, not quite enough to get us farther on this particular open problem. So let me talk briefly about some of the easier cases. Positive reducibility is no negations. So everything can be written in a big conjunctive normal form. All of my tables look like an and statement with a bunch of or statements and then positive literals. And that's very helpful, the fact that I'm just grabbing literals, grabbing bits from X and not changing them at all. Possibly I could get enough control to force this to be 1. What would that look like? Well, if an or statement is true whenever a single one of its letters is true. So if I can just guarantee one of the bits in each of an or statement, each or statement in a table, I could force the whole thing to be true. All my ors would be true, so my and would be true. But I can only ever control one half of my real, trying to fool this reduction. I have to make one half of it random, and the other half I have full control over. So let's try to control the even half. Let's suppose that there are infinitely many tables where I'm going to be able to find control. I'm going to be able to find an even literal in every single or statement. If that's the case, I can very bluntly just set all the even bits to 1, and I'll have to make the odd bits random. Now, as I mentioned, this is going to model that table because my conjunction is true because all my disjunctions are true. And crucially, if I'm using A, right, if it's preloaded, it's computable to go figure out which of these tables have this property, because my list of tables is computable, and tables in the reduction is computable, and this property of having certain bits be even is also computable, because all of the variables I can check. And so now, on those places where I have an even literal, I know, given A, that I'm going to output 1. Because I've forced all of them to be 1. And so this particular output would fail to be immune. It would have an infinite computable subset, so it can't possibly be random. So then perhaps this is, not trivial, but not too deep, because positive reducibility is fairly weak in this sense. I don't even have negation. But this is only one case. There's another case, right? Maybe I can't do this. Maybe I can't get all that control. Maybe every single time I try, one of my disjunctions contains only odd literals. Well, that's okay, actually. I could just set all the odd bits to 0 and make the even bits random. And this is going to be a theme that comes back, that if I can't get control over the even side, I kind of get a different kind of control over the odd side. So now some disjunct has only odd literals. And all of those are 0, so it's false. So my whole and statement has to be false. And this is happening for almost every table. This situation is even worse. And not just that it's not immune, but it doesn't even have infinitely many chances to be one. The whole thing's finite. There are only a few tables where this thing could possibly output 1. And so if it's finite, it's computable. So that's pretty much the argument for positive reducibility. There are 2 more cases that I haven't listed, right? Maybe I get control over the odd side, or I fail to get control and I go to the even side, but that's just changing some words around. And I changed the definitions very slightly, and it's exactly the same argument. So let's go to linear reductions next. Linear reductions are big XOR statements, and they're linear in their inputs. So anytime I have a variable, if I were to change its value, flip its bit, the entire output would change, because that's how my chained XORs end up operating. So I need a new definition to talk about this. I will say that a bit is fresh if I've never seen it before. Never used, brand new bit, that it has not occurred in any of the earlier tables that I looked at. So first of all, if my linear reduction or any of these reductions, if they only query finitely many bits, we're kind of host. We can't go fast, we can't go far enough. They don't have enough use to really give us something non-computable, because I could just give it this finite chunk and that would give me the whole ball game. So I can assume I can always find a fresh bit. There's always going to be a table that queries some bit that I've never used before. And just having one of them is enough to control the whole ball game. So let's, without loss of generality, let's say those fresh bits, they have to fall infinitely often in one parity. Let's say that parity is even. So as I mentioned, changing any of those bits changes the whole table. So when I encounter one of those tables that has a fresh bit, I can control it to ensure that the entire table outputs 1. All right, so really, I'm going to build up in stages. I've built so much of the real at stage S, and then I search for another table that has a fresh bit, and then I control that bit to control that table, and then I continue onward. Again, I have to be a member of either MLR that I'm feeding this, so I have to give an odd. The odd half has to be random. And once again, this search for even bits is computable. If I'm guaranteed there are infinitely many fresh even bits, then I can computably search for them. And if I can do that, then I will find infinitely many inputs where the table outputs 1. So the reduction, the output of the reduction will fail to be immune, and therefore can't possibly be random. So there are a few things that keep coming up that I want to give language to. First of all, the set of variables of a table, I'm going to call Q of n for queries, because in what's upcoming, I can't just control things by one bit. I may need to use more of the input. So I can't just talk about a single bit. I need to talk about the entire collection. And let's talk about what it means to control a table that I've been using implicitly on the previous slides. Some subset C for control, right, controls a table if there is some truth assignment, maybe not every truth assignment, but some assignment of C to force the table to be true. So for instance, if I have maybe P or Q implies R, there's a couple of sets that could control this. PQ could control it because I could set them both to be false, and now a false proposition proves everything. Or I could make R true, and now no matter what P and Q are, the entire formula is true. So there are maybe multiple sets. They could be disjoint, they could be mixed, that are able to control a table. And so our strategy for bounded truth table reductions, where we are allowed any type of table, we'll use those two ideas that we've been seeing. One is that we can computably search to try to find fresh bits that we haven't used before. And then we're going to try to control them to force our reduction to do something to fail to be random. I could, in principle, only search for tables that have a control set that can be controlled by a set of fresh bits. That I guess that would be enough, but the proof is much cleaner if I just search for tables that all their bits are fresh altogether, never been used before. That is a much better way to organize the argument. So towards that end, let's look at that first. Let's talk about this computable search that I've been doing. And then when that succeeds, we'll try to do the assignment. So to begin with, actually, before we even get into the computable search, we're actually going to do an induction. The base case is really easy, so we should go ahead and start there. We could assume, I guess I could do C equals 0. C is my bound on the number of variables I'm allowing in my table. And I need to show that bounded truth table reducibility fails no matter what my bound is. So I could start at C equals 0, where the only things my table does are output true or output false, which clearly can't work. But towards giving us the intuition for the rest of the proof, I want to start where something interesting is actually happening. So we'll say that it's only true or false finitely often. That's the sort of trivial case. And we'll induct starting with C. Well, this is really, really similar to the linear reducibility case because every table only has one variable. So I can control a table by controlling one variable. Right? It's not quite as lucky as XOR, where the table had many variables, but one variable sufficed. This works because the table itself only has one variable. So if I infinitely often can find a fresh bit, then I'm able to exert this control. And if I can't, then as I mentioned before, the whole thing must be computable because I'm only querying so much use. So I'll assume that it's infinitely often getting us an even bit. I'll control them. I'll set the odd bits to be random, and the computable search will always find another. So this really is just like the linear reducibility proof, but it's the base case for our induction now. So very helpful that we did the easy case earlier. Now let's assume for induction that I've gotten this to work for in a strong inductive sense, that for any reducibility, any number of queries any bound for queries less than C, I can find a real to defeat that reduction. A real that is one half of it is random, but the output under that reduction will not be random. So I want to give a little bit of language to the algorithm I'm using to do the search. And it's just the naive greedy algorithm. We don't need to do anything particularly clever. We'll just start with the most simple, start with the first one. Certainly those bits have never been seen before because I haven't seen anything yet. And then I'll just ask, hey, what's the next reduction? What's the next table that has all fresh bits? It's possible that maybe picking that one eliminates some future choices because their Q sets intermingle in a certain way, but I'm not going to worry about backtracking or anything. I'm just going to naively search in a greedy way. And if that succeeds, I'm golden. I'm in really good shape. I'm set up well to try to control those bits. But it's possible that this doesn't even succeed. It's very possible that my search can't even get off the ground. And I need to make sure that I can still defeat the reduction in that case. So this is where our inductive hypothesis comes in. If my search fails, I've gathered up all of these, some bound n I've worked my way up to. And after that bound, I'm never able to find another integer that has this nice property. So all of the information that I've been querying up to n must be getting used over and over again. Because if there were some query, if there were some table that never used any of this information, that would be all fresh bits. But that doesn't happen. So everything out in the future is going to ask a question about one of these bits h. And I'm going to call this h because I want to hard code them. It's finite information getting used a lot, so I may as well bake it into my reduction. And if I do that, I'm not really a BTTC reduction, am I? I'm not really making use of my full C queries. There's always a query that is asking about basic known information. It's really some D for bound less than C, which is my inductive hypothesis. Great. So let's do that a little more formally. I'm going to take all the tables that I already have for my truth table reduction, and I'm just going to build a new collection of tables where whenever I would ask a question about one of these bits, one of these hard-coded bits, I replace that propositional variable with falsehood and get myself a new reduction that acts pretty much identically to my original, as long as they don't see any ones, right, in that set H. So psi doesn't care. Psi doesn't ever ask questions about H. It will behave the way I want it to. Phi, on the other hand, might actually ask questions about H because those propositional variables haven't been replaced. So to make sure that doesn't break anything, I just want to make sure the reals I look at have zeros there. because having a 0 there is the same thing as putting a falsehood in for the propositional variable. I'm just kind of doing it in a different order depending on the reduction. So now this new psi, very specifically, I can see if I go and get my hands dirty and look at the tables, they all have fewer than C propositional variables because I've replaced a bunch of them. And so my induction hypothesis immediately guarantees me a real that will defeat that reduction psi. That output will not be random. So unfortunately, B might have those ones in it. I may have to change it a little bit. I may have to delete those ones, but H was a finite set, and being random is closed under finite changes. So I will change at a few bits in my oracle, but it will the half of it that was random before will still be random. And so since now I still have an input from either MLR, and my outputs are the same. And from the induction hypothesis, I know they're not random. So that's really where the induction is helpful. I initially, when I got started on this problem, tried doing, trying to do it by hand for okay, the truth tables with 2 variables, the truth tables with 3 variables. But very quickly, there's a combinatorial explosion where there are, 4,000 truth tables with 4 variables, and induction seemed like a much more elegant way to go. Okay, this is where the search failed, where I couldn't ever do what I wanted. So I'm left with the nice case. I saved the best for last. I have access to a computable set of indices. It was a computable search where all of their uses, all the queries they make are completely disjoint. So I'm going to try to control them. And maybe the good case, I have enough control. I'm always able to find some subset that only has even bits that controls the entire table. So because they're disjoint, I can set their bits without issue. I can fix them to be whatever I want and ensure that for those tables, my reduction will output a 1. I'll have to set the odd bits to be random, of course. And now the greedy algorithm does the work for me. I can computably search for tables that have disjoint use. I know I'll find infinitely many. I can computably check those tables. Do you have a set that controls you? And I can computably check those sets. Do you contain only even bits? So all of this is computable. So immunity must fail. But there's one case left in my last couple of minutes here. Maybe I can't get that control. Maybe no matter what I do to the even bits, there's always a way to mess it up. I can't ever force it to be 1. So I may as well just make the even bits random since they're messing me up. I can't actually use them to get what I want. But if I look carefully at negating those quantifiers, no matter what the even bits are, there must be a way for the odd bits to force the table to be false. And I've given up on the even bits. I've made them random. I'll just control the odd bits to do that. So if I can't force the even bits to be 1, I'll force the odd bits to be control the odd bits to force the output to be 0. And now phi can't be co-immune. And I really make use of the fact that randoms are supposed to be bi-immune. The complement shouldn't contain any computable set, but I've just demonstrated that it does. So I have a final few remarks here. The truth table reduction that I did much earlier, that generalizes really nicely to any number of finite columns or even the infinite case. There are computable ways to search to try to do this searching through and guess at the constant and guess at the random. And the proofs I just did are about bi-immunity. They show that this technique of using that half of a KL random is ML random is not going to be enough to strengthen, unfortunately. None of the reducibilities I looked at that are weaker than truth table could witness this reduction. It may well be witnessable by a different technique if we replace this with KLR on the right, but using this technique is not going to be enough. But what it is enough to do is talk about other bi-immune classes, like 1 generics, for instance. So for free, I get that this result for either 1 generic, because 1 generics are also bi-immune. So finally, there's a couple of questions here. The things I've just listed, it may still have a strong reducibility between them, but it will not be positive, linear, or bounded truth table. So there's still a question there that we haven't looked into too deeply yet about whether you could use a Turing reduction or maybe even a truth table reduction. And of course, the other remaining question is, well, okay, we ruled out this technique for talking about reducibilities in these math problems, but what else could we possibly use? Because if it turns out that those are equal, then there should be other reductions. So the hope is that maybe towards proving they're equal, we might be able to choose some other technique to make those reductions work and kind of work our way towards altogether showing those math problems really are the same. Or that proof could come from a totally different part of algorithmic randomness. We don't know yet. That is all I have for you today. thank you so much for having me.
Thank you, David. Thank you, David. So, other questions? Anything in the room, Stefan?
Nope, but it was a very nice talk.
Yep, absolutely.
I have a question.
Yep. Go for it.
So I guess this didn't really matter that much for the talk, but what is KL random?
Oh yeah, it didn't really matter, did it? So Martin-Low randoms are CE martingales can't work as a betting strategy. They have to bet in order, and they will not be able to win in the infinite limit. But there's a critique of that CE martingales maybe aren't what we want to work with. That seems strange that randomness should be defeating CE-ness. Randomness should be defeating computability. So maybe we'll work with computable martingales instead. But of course, computable martingales are CE. So the tweak there is that they are allowed to bet out of order. They are non-monotonic betting strategies. And there is a result that certainly if you can win using a non-monotonic computable strategy, there is a way to win with a CE strategy. So if you are not KL random, you are not Martin-Low random, and then we flip around to get the subset inclusion that we wanted. But it's still open if that reduction goes the other way. If winning with a non-monotonic strategy guarantees that I can win with a CE monotonic strategy. That's the easiest way for me to think about it. It's not actually how I tend to work with these things. I much prefer Kolmogorov complexity, but for the definitions, I think it's easier to talk about in terms of CE and computable martingales.
Any other questions? Yep. If not, let's thank David again.